for this lecture is focus on several stunning examples of profound mysteries that plague the deepest thinkers of the day, but ultimately got explained. There was a single biggest scientific mystery of the 19th century. It preoccupied the greatest minds of that period. And what it related to was at the core of our understanding of space itself. What's behind it? Well, we know that waves require some kind of material medium through which to travel. And the best and most common example of a wave is sound. Sound moves through air, but if you take away the air, it cannot propagate. You may have remembered this experiment. It might have happened in your high school science class. You have a ringing bell, and you enclose that bell in a glass container, and you start pumping the air out of that glass container, and the ringing bell gets dimmer and dimmer and dimmer to hear. And at some point, you don't hear it at all. You can still see it clanging away. That's evidence that sound cannot pass through the vacuum that we just created. Well, if light is a wave, then it too must require some kind of medium through which to travel. Here's the problem. Empty space is a vacuum, and we know that light reaches us from empty space. The moon is in space, the sun is in space, the stars are out in space, and there's a vacuum between us. So it was hypothesized that no, there's not air out there. There's got to be something, some substance, some medium that allows for it to propagate. And we gave it a name. We, by science ancestors of that period, we gave it a name. It was called the ether. The ether. We ought to be able to measure it. Two scientists came along. This is in the late 1800s. The physicist Albert Michelson and the chemist Edward Morgan, two American scientists. And they got together, collaborating, and perfected a new kind of tool called the interferometer. It's a special instrument that allows you to measure with high precision distances and speeds. And so in 1897, they conducted what came to be known as the Michelson-Morley experiment. So here's what they did. They said, all right, here's Earth. I'm going to measure the speed of light with the movement of Earth around the sun. Then I'm going to measure the speed of light against the movement of Earth around the sun. And if there is an ether out there, I ought to be able to show that the light added to Earth's movement, and I measure the speed of that, I'll get the speed of light plus the speed of the Earth. And coming back the other way, if I make that measurement, I'll get the speed of light minus the speed of the Earth. That makes complete sense. Of course it does. If you're riding in a train, back then it would have been a train, not a car. If you're riding in a train that's going 30 miles an hour and you send something forward 10 miles an hour, you add them, that object is moving 30 plus 10, 40 miles an hour relative to the ground. Come back the other way and you throw it out the back end of the train, that speed will be 30 minus 10, 20 miles an hour relative to the ground. It's that simple. That's all they were trying to do with the speed of light. Upon conducting this experiment, what they found is that the speed of light was the same no matter where they made the measurement. And this was astonishing. It was the greatest null result ever found for a scientific experiment. The null result is you expect to find some kind of measurement, and you don't. Usually, those experiments are like not interesting. But this was the most interesting null experiment ever conducted. And so, what do? Everyone knew there had to be an ether. So, there were a couple of guys who said, all right, we can solve this. There's a fellow named Lorentz and another one named Fitzgerald. And they got together and said, we know what's going on, because there's got to be an ether. Your measuring tools have contracted in the direction of motion. They've physically contracted. to fool you into thinking that you're getting the same speed of light. That must be going on. Just think about that. So embedded were they in the existence of the ether. The ether, this traditional concept that a wave requires a medium, that they would not even entertain the possibility that there was no such thing as an ether. They would rather assert that something odd was happening to your measuring devices. They were trying to rescue the hypothesis of the stationary ether. Now, we happen to know that physical materials can't just physically contract. That's not how they behave. They never behave that way. What we would later learn, not just a few years later, is that light, in fact, does not need a medium after all through which to propagate. It is a self-driven wave, a combination of an electrical wave and a magnetic wave. It was an astonishing revelation of the day. No ether. And what state of mind, though, allows us to recognize that the speed of light remains constant? Albert Einstein to the rescue. 1905, special theory of relativity. What he noticed was that those equations that would shrink your physical objects that are doing the measurements to conspire to give you the same speed of light, what Einstein showed is, no, they don't actually shrink. What happens is, the speed of light is actually constant. It's actually constant. And what's going on is that the rules of special relativity change how you end up making that measurement while you're doing it. And when that comes about, you find that the ether is not necessary, the speed of light is constant, and we have walked through a proscenium in the history of science where the ether was the last grasp, the last bastion of classical physics before the 20th century would open its doors. Because in the 20th century, what we came to learn is that whatever was your common sense that you were invoking about how the world must be, 20th century science and onward entered a time where, in fact, in order to understand the universe, at least some of the time, you had to abandon your senses.